Welcome back to ECE 320A. This video we want to start working with combining input signals and transfer functions to try to understand maybe a little bit more intuitively what's going on in the S-plane and relate that or connect that with what you might expect in the time domain. And so we're trying to have as our goal in this video the establishing a connection between a system's output response and what you would see in the S-plane diagrams, and in particular, what poles are there in the S domain, and how do we relate those to what's going on in the time domain. In order to try to make that relationship a little bit stronger, I've tried to split the page into two pieces. And when you're on the left-hand side of the page, we're in the time domain, or blue, and I'll try to be color coding this properly. And when you run over to the right-hand side, then we're in the S domain, we're in the frequency domain. And as electrical and computer engineers, you want to become very comfortable thinking or understanding concepts in both the time domain and the frequency domain, and have a good connection established between those two domains, or a good relationship between what's happening in those two domains. So we have the time domain and the S domain, or frequency domain, and let's look at this connection between transfer functions, input waveforms, and outputs relative to a very classic system, a passive low-pass filter. And I think if I were to say, give me a transfer function of a passive low-pass filter, you could quickly sketch the S-domain circuit diagram that you now should be very comfortable with. You could then perform the voltage divider relationship to find how the input is related to the output in this system or in this circuit, and simplify that to find the pole zero diagram, where we have 1 over RC over the denominator expression S plus 1 over RC. That we now have in the frequency domain, or in the S domain. We can now go back into the time domain and say, well, what's the impulse response of that system look like? Or if I now put in the time domain X, if I hit X with an impulse waveform, what am I going to see at the output Y? And remember what an impulse response does. The impulse waveform really just energizes the energy storage devices in the circuit. So we've now charged up the capacitor, and beyond t equals 0, we now want to see how does that energy dissipate in this circuit, or what does Y of t look like once we've energized that energy storage device. What is H sub 1 of t? So it depends on what elements we have in the circuit and how they are interconnected between the input and the output. Well, to find little h sub 1 of t, we can simply inverse Laplace transform capital H sub 1 of s. And that's pretty straightforward, because we now have just a gain 1 over RC weighting a 1 over s plus a pole. And that 1 over s plus a pole then in the time domain looks like e to the minus pole location, which in this case is 1 over RC times t, and this is true for t greater than or equal to 0. That's now what we have for our impulse response, and we could rewrite that in a little bit different way. We could say, well, the gain, or the constant, isn't going to change. We still have a 1 over RC, but we could combine the t and the RC to where we have a minus t over RC, where we now have e to the minus t over tau, where tau is this time constant RC. And now hopefully you can see that if, in fact, RC is selected to be a particular value, tau, then this exponent e to the minus, or this exponential factor e to the minus t over tau, when little t, time, is equal to tau, then we have e to the minus 1 weighting 1 over RC. And e to the minus 1 is roughly 0.37. So after one time constant, we're 37% of where we started at time t equals 0. And you can now just march through different time constants by letting t be 1 tau, 2 tau, 3 tau, and you're seeing that you're weighting 1 over RC by e to the minus 1, e to the minus 2, e to the minus 3, etc. So let's pick a value for 1 over RC. Suppose that we let 1 over RC be 10, so that we put a pole at a value s equal to minus 10, or h sub 1 is 10 over s plus 10. Well, what have we just done? Now we've said that 1 over RC is equal to 10, or RC is equal to 1/10. Taking that into the time domain, then we see that we now have, if 1 over RC is 10, we have 10 e to the minus, and 1 over RC was 10, so we have e to the minus 10t, t greater than or equal to 0, and that was when RC was 1/10. This is now what we have for time domain and frequency domain. We now have one pole at s equal to minus 10, and we can now plot that in the s-plane. We can now say, oh, I have a pole over here. Let me just guess where that is. Let's just say there's minus 10. I now have a single pole at minus 10 from my transfer function h sub 1 of s. What do I have for h sub 1 of t? Now, in terms of behavior, what's my time constant? My time constant, tau, I said I was going to color code this, tau is now 0.1. So let me say that this is now 0.1, 0.2, 3, 4, and 5. So now after 0.5, I should be basically at 1% of where I started. And where am I going to start in terms of a numerical value? Well, when t is equal to 0, I have 10 e to the minus 0. E to the minus 0 is 1. I'm starting up here at 10. And in one time constant, I'm 37% of the way down from that. I'm just going to guess that. And then I'm at about 14%. I'm going to guess that. But by the time I get to 5 tau, which is 0.1, 5 times 0.1, or 0.5, I'm now basically down to nothing from where I started. I'm really down at 1% of 10, which is then a tenth for my value. You can do a better job of sketching this, but this is now, and I've overemphasized where I'm at beyond 1/2. After 5 time constants, I'm effectively at 0. But this is now the connection between a pole pattern in the s-plane, a pole at minus 10, and what that looks like as a impulse response. And what's that mean? Well, that now says that if I hit or excited this circuit, this low-pass filter, with an impulse at time 0, then what you're going to see at the output is exactly what h sub 1 of t is. You're going to immediately be charged up to 10, and then you're going to trail off rather quickly down to 1/10, 1% of 10, which is 1/10 in value relative to, for the 10 starting location, at 5 time constants, or 0.5. That's what happens to the impulse response, or that's the impulse response of this low-pass filter. What if, in fact, we excited this system with something other than an impulse waveform, and let's say that we excited it with an exponential decay, where now we look at e to the minus 2t. U of t is now a switch, so this just says we're looking at e to the minus 2t for non-negative values of time. And what does that look like? Well, at time 0, e to the 0 is 1. Then e to the minus 2t, well, what is 2 in the exponent? We now have, if we wanted to look at this, you can look at it many different ways. X of s, capital X of s, if we Laplace transform this, is now 1 over s plus 2. We have a pole at minus 2, and that's right here. There's our pole, and our tau is whatever needs to be if we wanted to look at e to the minus t over tau. What does tau have to be in order to end up with e to the minus 2t? Well, tau equal to 1/2 would do that. So now in this case, if we said that this particular point is now 1/2, here's 1, here's 1.5, here's 2. In 2.5 units of time, we now are going to be at 1% of where we started, which is 1, so we will be at 0.01 in terms of a value. So our input that we're exciting our system with will be this exponentially decaying waveform, not an impulse, and we want to know what happens to the output of our system when we excite it with this exponential, and if we hit our system with an impulse, this is what it would look like. So now we're wanting to basically convolve x of t with h of t. So in the time domain, we have h of t convolved with x of t, and maybe you don't see what that looks like, but maybe it's easier to think about what's happening in the frequency domain, because now what is y of s? Y of s is simply h of s times x of s. But h of s was 10 over s plus 10. So now we have 10 over s plus 10, and capital X of s was 1 over, whoops, I'm anticipating what x is before I even get there. X was 1 over s plus 2. We now have a pole at minus 2 and another pole at minus 10, and those two poles, one is due to the system pole is at minus 10, the other pole is due to the input waveform, which is at minus 2. Now we have two poles, but those two poles will play together or sing in order to produce our output waveform, little y of t, and we can find little y of t by inverse Laplace transforming capital Y of s. So let's now look at inverse Laplace transforming y of s. We now have two real poles, another reason why we wanted to start learning how to inverse Laplace transform, and we can do that by partial fraction expansion. We now have two factors. It's strictly proper. If we were to find these partial fraction expansion coefficients, we would find that each has the same absolute value, 10 over 8, or 1 1/4. But now the 1 associated with the s plus 10 factor is actually a negative 10 over 8, or 1 1/4. If we now have those partial fraction expansion terms for capital Y of s, we can fairly easily take this into the time domain. What's the inverse Laplace transform of 1 over s plus 2. Well, that's just e to the minus 2t. And that's scaled by 10 over 8, or one and 2/8, and 2/8 is 1/4, so we have 1 1/4. We have 1 1/4 e to the minus 2t minus the piece associated with 1 over s plus 10, and that's just e to the minus 10t. And again, we can weight that or switch that on by scaling that by the unit step u of t. And what's this look like? Here's what it looked like in the frequency domain. We had two poles at -2 and -10. That now came into the time domain. We ran over to the left-hand side of our paper, and that's now 1.25 scaling e to the minus 2t minus e to the minus 10t. And you can see that these have two different sort of rates to them. E to the minus 2t is not going to decay as quickly as e to the minus 10t, but they're both starting with, one is starting with a positive 10 over 8, or 1 1/4. That, let me say, is the e to the minus 2t, and that's going to now come down, and it has a time constant of 1/2. So in 1/2, it's going to be 37% of 1 1/4. Then it's going to trail off, and after 2.5 units of time, it's gone. We're subtracting from that the e to the minus 10t, so after the time constant there, here our time constant is 1/10. Here our time constant was 1/2. And I would maybe then venture to say that this is our slow time constant, this is our fast time constant. So in green, after 5 of those, 5 1/10ths, or in half of a second, we're now gone. So that if we now take and subtract the green from the blue, we're going to generate what actually is happening in y of t, which at 0 we have 1 1/4 minus 1 1/4, so we start at 0, but then we take and subtract the green, which is disappearing rather quickly from the blue, and after 0.5 we're basically on top of the blue curve because the e to the minus 10t has vanished. So the red curve illustrates y of t, and our slow term is what dominates after the fast term has appeared and disappeared, and that will disappear after 5 of the fast time constants. That's our fast pole. And our slow pole is at e to the minus 2. I'm sorry, associated with e to the minus 2t. The slow pole is at minus 2. This is our slow pole, and this is our fast pole, and our slow pole is closer to the imaginary axis. It is, in absolute sense, smaller in magnitude than the e to the minus, or the pole at minus 10, and so it's going to decay more slowly than the pole at s equal to minus 10. And this, now, if we wanted to comment, this is now 5 times tau slow, which is our dominant mode behavior. So the slow pole is going to dominate the response, and so that's giving rise to our dominant mode behavior. And the red now, after the fast dynamics disappear. The red now follows the blue, and this is what would happen if we applied an exponentially decaying waveform x of t to the input of a low-pass filter that has a time constant of tau equal to 0.1. Those play together and produce then this waveform for an output little y of t. That now is combining these two poles in the S-plane. And you can see that if we hit it with a different exponentially damped waveform, that would introduce its own pole, whether that's relatively fast or slow compared to the system's dynamics, which are governed by a pole at -10, will depend on where this exponential pole lives in the S-plane. What happens, let's look at this for a different kind of input. What would happen if we applied not an exponentially decaying waveform, but what would happen if we were to apply a sinusoidal signal? What happens if we shake this system at a frequency of omega naught? What's capital X of S? If we take and Laplace transform little x of t, hopefully you're starting to almost have these tables ingrained so that this now becomes AS over S squared plus omega naught squared. And if we had our same low-pass filter, which had a pole at -10, what's going to happen when we excite it with a sinusoid? Where are the poles located for this time domain waveform little x of t? If you find the roots of the denominator of capital X of S, you will find that you now have complex, purely imaginary poles at omega naught and minus j omega naught. Those will now give rise to a y of S that has not only this fast pole at -10, so we would have a mode of e to the -10t, which will decay in half of a second after 5 time constants, but we will also have poles in y of S corresponding to these poles on the imaginary axis, and those do not decay with time. They just continue to shake. So we will see that the output response little y of t, when a system is excited, a linear time invariant system is excited by a signal that's a sinusoid, in this case a cosine, we will see that system actually shaking at the input frequency of excitation, which is omega naught. And we will have then terms in capital Y of S associated with poles at plus and minus j omega naught, and that will give rise to then a sinusoidal waveform in the output at the same frequency as we excited the system with. We will just have the amplitude may be modified and the waveform shifted in time slightly, and that's where we want to head in our next set of videos.